Hi, in this video, we want to take a look at synthetic data. All right, so what we want to do, we want a deeper, more intuitive sense of what synthetic data is, what it looks like. What is the output that we get when we do this? All right, so what we're going to do, we're going to go through, we're going to generate synthetic data for an imbalanced classification problem, and we're going to generate the data in multiple ways with different algorithms. Then what we're going to do, we're going to compare them visually with principal component plots. And here is the first principal component plot, just so that we can see it as an initial go, see where we're going. Now, let's go ahead and scroll up to the top so that we can see how I got this, so that if you're looking back, if you want to understand what I did, you got to have the code. All right, so synthetic data is a method of addressing imbalanced data. It's honestly like one of my least favorite techniques, but it's still a good thing to have in your tool belt. It's a good thing to have ready to go if you need it. It's good to have options, right? So I want to always have that option, but if I'm going to use this, I want to generate the best synthetic data possible for the problem I'm working on. All right, so here's our game plan. First, we're going to load the data, and we're going to do a little bit of modification on the data set. Then we're going to generate synthetic data. And then after a little bit of manipulation of the data to make the data sets more comparable, after that, we're going to plot the principal component scatter plots. And so that way we can visually see what's going on. And hopefully that'll give us a better understanding of what each of these do and which one we would prefer to use if we were going to use this in a real project. So let's go ahead and load the data. And so we're going to be using the yeast4 data set from the imbalanced package in R. And if you look through, all of the predictors except one is a numeric variable. This one is a 2-level factor. So you know what? I went ahead and I converted it to binary. So if I have synthetic data and the value is between 0 and 1, I know that really that's like a modeled likelihood of it being 1. And so I'm okay with that not actually being the correct value. Now, if I get a value greater than 1 for synthetic data or less than 0, then I might want to consider trimming it back down to 0, 1. All right, so let's go ahead and generate the synthetic data. So one thing I'm going to do, I'm going to use set seed of 823, and I do this so that I can reproduce these results later down the road if I want. Most of these methods are going to be using some kind of random number generator. And since there's a random number generator involved, I should, as best practice, set the seed beforehand. Now, on my machine in R, I have all of the random number generators set on the default settings, so that if I was to hand this code to someone else who is using the same version of R as I am, and they have not tinkered with the settings of random number generators, they should get the same results that I get. All right, so what I'm going to do, I'm going to store all the data in a list. I'm going to call it list synthetic. And so this way I have my workspace all nice and clean and organized, and I'm able to iterate over these data sets when I have them stored afterwards. So first one we're going to do, we're going to go ahead and use the ROSE algorithm from the ROSE package. And there's a classification of positive or negative in the data set. We're using all the predictors available. So what I'm going to do, what this does, this formula says that every column that's not class is a predictor variable to be used to predict class. And so what it's going to do, it's going to generate class and all of the predictors with this dot. And here this says N is going to be 2000, and this says what percentage is going to be the minority case, which for us is going to be positive. And I set my seed. And now this is different than setting seed up here because this is inside the function itself. Next, we're going to use the data mining with R package, which has a textbook associated with it. Good book to work through if you're interested in the topic. And we're going to go ahead and go with Smote. Now, we're going to be using Smote twice from 2 different packages. It'll be interesting to see what's the difference between them. And, so perk over, this is the oversampling percentage that we will get. K is the number of nearest neighbors used, and perk under is the percent of undersampling for the majority case. Now the rest are going to be from the Smote family package. The first one we're going to do is just Smote. So this is our second version of Smote. And we specify the predictors, then we specify the target. And we do that every single time with a Smote family algorithm. Then there are other parameters for each individual algorithm, each individual function, but for here, I just worry about the number of observations, if that's an option to mess with. And then I don't mess with anything like nearest neighbors or any of the other possible parameters. I keep it on the default setting because otherwise this video will get really complicated. So here we have 100 observations. Now, the ADAS function does not give us an option for increasing the synthetic data size. It takes a look at the original data set, and it uses the size of the original data set to judge how much data should be generated. And then we have the ANS function in Smote family. Then we have BL Smote. I think it's best linear. I can't remember. Then we have RSLS algorithm, then SLS algorithm. Then we have density-based Smote. Okay, so all this code did was generate the observations for us. And you'll notice that in the Smote family, every single time I'm specifying, give me just the synthetic data. Why? Because for this video, we're just looking at the data. We're not worrying about the other features. All right, well, it works out that sometimes data is data that we don't want is generated. Sometimes it is. And so we need to make sure that we only have the synthetic cases that we care about, the minority case. So we only want examples that are positive for this video, just so that things are more uniform and comparable. And so we go through, and first thing that we do, since we get different column names, like the Smote family likes to have class as lowercase class, which I don't really know why, but it's all lowercase. To make everything consistent, I go ahead and I change all of the column names to the column names coming from the original data set. That way, the column names are uniform. Now, next, some of the Smote family algorithms don't give us factors like we had in the original data set. Well, the original data set is a factor, 2-level factor. So I go ahead and convert it to be the same format as the original data. And now here is where I'm actually filtering out. Now, these algorithms are inconsistent on the number of observations that we get back given the parameters we put in. So I go ahead and I remove a lot of the observations just so that I have the same size in each of my synthetic data sets. This way, I'm comparing apples to apples when I look at those plots. If I had a very sparse plot and then one that was very heavy on points, it's not comparable, because the heavy one's going to have so much gunk on the plot that I won't be able to tell what's going on, even if that's a better or worse method than the sparse one. And now here, what we do, we go through and we tack on the negative observations from the original data set. That way, when I go through and I plot, I can see everything together in this manner. And then putting on a source onto each of the data sets lets me be able to connect the method or where I got the data later. Now let's put all the data into one big data set. The reason why we do this is so that I can pass it to ggplot and plot all of them at the same time. And then here, this factor statement is just sorting the source of the data just so that I have original in the upper left-hand corner. So now let's compute the principal components. Now you'll notice that I'm not centering and I'm not scaling the data. The reason for this is all of the predictor variables are between 0 and 1. So I feel like I don't need to worry about it. Since they're all the same magnitude, they're all the same nature. You could argue that it would be good to center and scale. I conclude that it's not necessary for this particular project. Now let's actually do the visualization. Here I'm defining the colors. And then I am loading ggplot. And now here I'm using ggplot to make the scatter plot. And what do we see? All right, so we have the original data here. We have the data mining with our version of Smote. We have rows, and then we have all the Smote family. Okay, so first thing that jumped out at me, you see this big old cloud of rows. Let's compare it to the original data. Let's compare it to this. Compare to this, compare this. This is much, much bigger. Any boundary I have between the green and the red here is completely smashed. So if I was to use this rows data set, the rows data set would be bleeding into, the synthetic data would be bleeding into the higher dimensional space of the negative observations. And because of that, I would have a lot of errors close to what would be the higher dimensional boundary if I was to do something like linear discriminant analysis. The boundary region that would be here is going to be bled over a lot. And so this would not be a good idea. Looking here, I feel like these will suffer the same problems. The data mining with our version of Smote, the ADAS and the ANS methods, I also feel like this is too much. This is filling in too much region. Because notice that there is overlap here. So, you know, when I look at this plot, I'm seeing, you know, that green in there, that I don't have perfect separation. And because I don't have perfect separation, I'm getting too much representation of the positives in the areas in between points of the original. Now, when so let's look at the Smote family over here. Smote family Smote and the data mining with our Smote, we can see that there's a difference. I would definitely prefer this version if I had to use the raw Smote version. Now, when I look through here, the ones that I'm liking, I like RSLS and SLS the most. Why is that? Well, because these are kind of like forming like tight little bunches. And inside these tight bunches, it's distinctly possible that we're getting good shells in higher dimensional space of points that are consistent with being positive. And so my machine learning algorithm will be able to work with these better. Now, the BL Smote is also a good guy. And so is density-based Smote. So these four visually look pretty good to me to work with. I personally probably would like one of the SLSs the most, but if you have a different opinion, that's all right. Now here we can look at the first and third principal components, and with regard to rows, the ADAS, ANS, and original Smote, I'm reaching the same conclusion. Here, let's see, what do I feel is the best? Yeah, I like these guys the most, maybe density based, but these four are definitely the ones that I'm preferring. The more it looks like a cloud, the less I think it would be wise to use. And here is the second principal component plotted with the third principal component. And I reached the same conclusion. I'm feeling the most love towards density based. All right, well, this is all I've got for you. Take care and goodbye.